This will be a walkthrough of the AQA GCSE Chemistry 2023 Higher Tier Paper 2. Question 1. A student investigated the rate of reaction between zinc and sulfuric acid. Hydrogen gas is produced during this reaction. Figure 1 shows the apparatus. So the apparatus is all labelled for us, except for this container. This is the method used. 1.1. Suggest why the stopper must be put in the conical flask as quickly as possible in step 3. So reading step 3, it says quickly put a stopper in the conical flask and start a timer. Well, what's actually happening in this experiment now is that they're going to collect a gas, as it says in step 4. And the gas has to be a result of the reaction between zinc and sulfuric acid. What's going to happen then is once the gas gets produced, it's going to go through our delivery tube and then into the container, and these bubbles that we will see in our measuring cylinder will be the gas that's produced, and that will cause the water to start leaving the measuring cylinder as it will start to fill up at the top of the measuring cylinder. So why do we want to put the stopper as quickly as possible? Well, we want to make sure that no gas escapes, or as little gas escapes as possible, and it goes through the delivery tube and into the measuring cylinder. So it's to prevent the escape of gas. (1.2) The student calculated the rate of reaction for each trial. Table 1 shows the results of the calculations. So the rate of reaction in each of these 4 trials was recorded. Determine the mean time taken to collect 20 centimeter cubes of gas. Do not include any anomalous results and use the equation. 5 marks. So we have to calculate a mean. So you should be taking values and then dividing by how many there are. But it says to not include any anomalous results. So we've got to look through these data points and realize which one is anomalous. Remember that anomalous means not fitting the pattern, or odd one out. So we have 0.78, 0.81, 0.68, 0.81. So the one that's the odd one out in this sense would be 0.68, as it's further away from the other 3. So we would exclude that from our mean. So calculating our mean then is going to be 0.78 plus 0.81 plus 0.81, and we're going to divide that by 3. So doing that, we get a mean rate of 0.80. Remember that the unit is going to be the same as that's in the table, centimeter cube per second. But what we want to find out now then is the time that's taken to collect 20 centimeters of gas. Now looking at this unit to find out the rate then, it's going to be volume divided by time, because that's always what rate is, it's something over time. So in this case then, our rate we know is 0.80. Our volume is fixed, 20. And the time is what we're trying to find out. So 20 divided by something will give us 0.80. So putting that into the calculator then, we would get a mean time of 25 seconds. (1.3) The student changed the investigation so that the mean time taken to collect 20 centimeter cubed of gas was greater. Which 2 changes would increase the mean time taken to collect 20 centimeter cubed of gas? Tick 2 boxes. So we're changing something in the experiment to cause the time taken to collect this gas to be longer. So if it's longer, that means the reaction is slower. So we want to identify two things from this list that's going to cause the reaction to be slower. Well, using a catalyst is going to increase the rate of reaction, so it can't be that. Using a larger conical flask won't have too much of a impact, so that's not correct either. Using a lower temperature, well, remember that temperature is linked to energy, so if we're increasing the temperature, we've got more energy for our reaction, so that should cause it to be faster because there'd be more collisions. So lower temperature would be correct. Using smaller pieces of zinc, that would mean that the surface area would be greater, and that would cause the rate of reaction to increase, so that's not correct. And then using sulfuric acid of a lower concentration means that there are less of reactants, so that means that the time taken to finish the reaction will be longer, so that should be correct too. 1.4. Hydrogen gas is produced during this reaction. Describe the test for hydrogen gas. Give the result of the test. So testing for gases, there are three you must be very, very clear on: hydrogen, oxygen, carbon dioxide, and then you've also got to remind yourself about chlorine and halogens. So, hydrogen. Well, for you to test for hydrogen, it's going to be a burning splint. Now, it's very important that you use the term burning because a glowing splint is what is for oxygen. So you need to make sure the difference is clear. But what will be the result of you having this burning splint with hydrogen? Well, burning splint with hydrogen will cause you to have a squeaky pop sound, which will occur. Question 2. This question is about alcohols and carboxylic acids. Alcohols are used as fuels. A student burned 1 gram of 6 alcohols and determined the energy released from each. Table 2 shows the results. So we've got these 6 alcohols. The formula is given, and the energy released for each one is also given. 2.1. Calculate the mass of ethanol that must be burned to release the same amount of energy as burning 1 gram of heptanol. So we're comparing ethanol to heptanol in this question. We're dealing with the mass. Remember that even though they're asking us for the mass of ethanol, we have to then think about 1 gram of heptanol, because that was the actual mass that was used in the question. So, if we've got 1 gram of heptanol, the energy that's released for that is 38.9 kilojoules per gram. We know the energy released for ethanol. That's 29.6 kilojoules per gram. We're trying to find out what the mass of ethanol would be to get that same amount. So for us to do that, we want to find out what's this difference, so how many times larger the energy released of heptanol is compared to ethanol. So the easiest way to do that is to just take 39.8 and divide that by 29.6. Once you do that, you just multiply your answer by 1 gram and you'll get your answer for the mass. So 39.8 divided by 29.6 will be 1.34. And of course, if you just multiply that by 1, it'll be the same. So our answer is 1.34 grams. The energy released in kilojoules per gram varies with the number of carbon atoms in one molecule of each alcohol. Plot the data from table 2 on figure 2. So figure 2 is our graph here. So we'll need to use our table as well as the graph to plot the results. Now, thinking about what's on our x-axis, it's the number of carbon atoms in one molecule of alcohol. So we've got to start with ethanol and look at the middle column in our table, because that gives us the formula of the alcohol. So with ethanol, it has 2 carbon atoms. So we're starting with 2 here, and then we've got to find 29.6 because that was the value in the table. So the good thing about this y-axis now is that the interval is 0.2. So we know that in the middle then that will be 29, and then we're just going up each line until we get to 29.6. So we place our point there. 3 is 33.6. So there. 4 is 36.1. So this one would be halfway between 36 and 36.2. 5 would be 37.7. So again, it's going to be halfway, so not on the line itself. For our hexanol, 6 carbon atoms, that would be 38.9, so just below 40. For hexanol, it's going to be 38.9, so just before 39. And for 7, it's going to be 39.8, which we used before, so just on that line below 40. (2.3) Estimate the energy released in kilojoules when 1 gram of octanol is burned. Well, we have to think about where would octanol go on our graph. Well, at this point now, what would be useful would be to draw a line of best fit and then see how that line would fit for octanol. So by doing a line of best fit now, it's got to try and go through the points, trying to be as careful as you can to meet the trend in the line. Now if we generate our line like this, all we would need to do then is find out where does that touch octanol. So it's touching octanol right at this point here. So if we read up then, it's going to be around 40.5 or 40.6. I think it's going to be closer to 40.6. So we can put that as our answer. Remember though, that people are going to read their graphs differently. So there is a slight range. So you want to think about a range of 40.4 to 40.8. So 2 above and below the value that we've just gotten here. (2.4) Carbon dioxide is produced when alcohols are burned. Carbon dioxide is identified by bubbling the gas through lime water. Complete the sentence. Choose an answer from the box. Lime water is an aqueous solution of. Well, lime water is a solution, but it's not a salt. So we've got to rule out the salts in our box. Calcium chloride is a salt. Calcium hydroxide is not a salt. Calcium nitrate is a salt. Calcium sulfate is a salt. So lime water is going to be an aqueous solution of calcium hydroxide. 2.5. Give the result of the test when carbon dioxide is bubbled through lime water. So another testing for gases question. Carbon dioxide now, yes, we add lime water. What are we expecting now? Lime water is a colorless solution until carbon dioxide is added to it, and then it will turn cloudy or milky. Ethanoic acid can be produced from ethanol. What is reacted with ethanol to produce ethanoic acid? Tick one box. Well, ethanol and ethanoic acid are our two substances that we're interested in this question. Now, what's special about these is that they have functional groups, unique groups that allow them to be identified. With ethanol, it has the group OH. With ethanoic acid, it has the group COOH. So, the difference really, because both of these are going to contain carbon and hydrogen atoms, the difference really is that in our carboxylic acid, there is an additional oxygen atom. So we need to think about how this is going to be added, or what is going to add it. Well, a halogen is not going to help with adding an oxygen atom, so it will not be a halogen. An alkali metal, same thing, not going to help in our functional group. An oxidizing agent, well, if an oxidizing agent is used, an oxidizing agent will add oxygen or remove electrons from a substance. So in this case, that does match what we've been showing here. And water, well, water is H2O, so it does have an oxygen atom, but water is usually used to split things. So in this case, it's not going to be the correct answer, so it is an oxidizing agent. 2.7. Ethanoic acid contains the functional group COOH. Complete the displayed structural formula of this functional group. So we reminded ourselves of the functional group of ethanoic acid previously already, so we just need to now display the correct formula for it. Now, drawing this out properly, and we can use an example of ethanoic acid. Ethanoic acid would have this structural formula. So all we need to do now is show this in the space below. So there needs to be a carbon atom which is double bonded to an oxygen atom, and then the carbon atom also has a single bond to an oxygen atom, and then that has its bond to a hydrogen atom. (2.8) Ethanoic acid reacts with different compounds. Draw one line from each compound to a product of the reaction of the compound with ethanoic acid. So, essentially what the question is telling us is we've got ethanol, we're going to react that with ethanoic acid, and we're looking for a product. Sodium carbonate, we're going to react that with ethanoic acid. We're looking for a product. Well, what's ethanol an example of? Ethanol is an example of an alcohol. What's ethanoic acid an example of? It's a carboxylic acid. So, if you have an alcohol and you react that with a carboxylic acid, you will make two things all the time. You'll make an ester and you'll make water. So what we need to do is we need to identify either ester or water in our products on this right hand side. While I am looking through, we do not see water. There is no word ester there, but when you have a specific alcohol and a specific carboxylic acid, it will make a specific ester. So looking at the name now, ethanol with ethanoic acid, it will make ethyl ethanoate. So here is our ester. And we can do the same thing for our second compound, and we should be able to try and obtain the correct answer. So, sodium carbonate. A sodium carbonate is an example of a metal carbonate. We know that we've got a carboxylic acid, but we have an acid that is used. So, we're reacting a metal carbonate and an acid. What do we form? We will always form a salt, water, and carbon dioxide. So we already established that water is not one of these products. We're looking for a salt, and there is no salt here. But carbon dioxide is there, and that is the product that we will always form. Question 3. This question is about chemical analysis. Potassium bromide is used in medicine. A scientist tested a sample of medicine to show the presence of potassium ions and of bromide ions. The sample is soluble in water. 3.1. Plan a method the scientist could use to show the sample of medicine contains potassium ions and bromide ions. The scientist has following piece of equipment. You should give the results of the tests. 6 marks. So planning a method, so we need to use the equipment, how we're going to use the equipment, what are the results that we're going to obtain. So we'll start with flame tests. So we need to remind ourselves now what pieces of equipment will be used in this flame test. Well, let's put an F next to each piece of equipment that will be used, and then we know that the rest will be used to test for the bromide ions. So flame will require a Bunsen burner, a metal wire. So we need to use those pieces of equipment when we're testing for cations, because that's what flame tests are for. Now, how does the flame test work? Well, we'll have our Bunsen flame, and usually within our Bunsen flame, when we're using flame tests, we usually put our sample in the hottest part of the flame, which is the blue, or this blue area. Now, the other thing that we're going to be using in this test is a metal wire which will contain our sample. So our sample will be on the end, and that is what we pass through the Bunsen flame. So the thing that I want to state first then is place the sample on the metal wire. Now what we want to make sure, so we know that the result is for potassium ions and nothing else, we want to make sure that this sample is not contaminated with anything else. So to make sure of that, we want to make the metal wire as clean as possible. Now usually what we use for that is hydrochloric acid or some strong acid to ensure that the sample is not contaminated. But it's not given in our list, so we don't need to include it. The first thing we want to say then is add sample to metal wire. Once we do that, we put metal wire through blue part of Bunsen flame. Now remember that we need to give the results of the test. So we need to remember our flame test colors at this point now. So with this potassium, it's going to be a lilac flame. So what we're looking for is a lilac flame, and that will confirm the presence of potassium ions. So now we're describing our bromide ions. And for that, we need to use nitric acid and silver nitrate. So the first thing that we want to do now, because remember that we've got a medicine, it could be a solid. We want to make sure that that's dissolved, because if it's not dissolved, the test won't work. So we need to dissolve the sample, and we just add the distilled water to dissolve it. Now, where are we going to be dissolving this? We're going to be doing this all in a test tube. So remember, we have to remind ourselves of the equipment that we're using. So dissolve the sample in distilled water in a test tube. Once we've done that, then we can start to add the nitric acid to our test tube. At this point, we shouldn't expect any color change yet. It's after our last chemical that we add, which is the silver nitrate solution, we will start to see something. So we're going to mention the pipette now, because we haven't mentioned that. We've mentioned the test tube. We mentioned distilled water. We mentioned the nitric acid. So we're going to use a pipette to add the silver nitrate. Now, what's going to confirm for us the presence of the bromide ions? Well, with these tests, we're looking for precipitates. In the case of bromide ions, the precipitate that we're going to be looking for is a cream precipitate. So just like in the flame test, we're looking for the color, which is a cream precipitate. And there's the answer to our question. Scientists could also use an instrumental method to show the presence of potassium ions in the medicine. 3.2. Which instrumental method could be used to show the presence of potassium ions in the medicine? Well, again, it's potassium ions. It's a positive ion, cation. So we're going to be using then flame emission spectroscopy. 3.3. Give one advantage of using this instrumental method instead of a chemical test. Well, if we're using instrumental methods, there are many advantages of doing it. As we said before when we were describing the method for flame tests, there is a chance that there could be some contamination if it's not handled properly, and this could affect the outcome of the result. There could be some overlapping of colors, so it may be difficult to tell, maybe a bit subjective. With our instrumental method, it's going to have less human error. So that means that our result is going to be more accurate. The flame test itself isn't too complicated. There aren't many steps involved. So you are able to get a result fairly quickly. But again, when you're using automated machinery, you are going to be getting results fairly quickly. So another option could be the fact that it's fast. Question 4. This question is about greenhouse gases and climate change. Carbon dioxide and methane are greenhouse gases. 4.1. Which of the following is also a greenhouse gas? Tick one box. Well, chlorine is not a greenhouse gas. Nitrogen is not a greenhouse gas. Oxygen is not a greenhouse gas. Nitrous oxide is a greenhouse gas, but not nitrogen on its own. So our answer is water vapor. Remind yourself, other than carbon dioxide and methane, water vapor is a greenhouse gas. In the past 50 years, there has been an increase in the world population, the concentration of carbon dioxide in the atmosphere, the concentration of methane in the atmosphere, the mean temperature of the atmosphere at the Earth's surface. Most scientists think this information can be used to explain climate change. 4.2. explain why the increase in world population may have caused the increase in the concentration of carbon dioxide in the atmosphere. So we've got to think about why an increase in the number of people on Earth has led to an increase in the concentration of carbon dioxide. Well, it's about how carbon dioxide can be released into the atmosphere to help us answer this question. There are numerous ways. One way is respiration. Combustion, which is the burning of fossil fuels. And a lack of photosynthesis. Because remember that a lack of photosynthesis will lead to less carbon dioxide being taken up. Now, we can't mention respiration because it wouldn't cause a drastic increase in the temperature, in the concentration of carbon dioxide. And as I was explaining about photosynthesis, that's still going to be there in quite a high amount. So that wouldn't cause a drastic change to the increase in carbon dioxide. However, combustion would. As we described it, it's the burning of fossil fuels. But why would an increase in the world population lead to more fossil fuels being burnt? Well, if there's an increase in the world population, more people need to get around as quickly as possible. So there's going to be need for more fuels to be burnt, because fuels operate machines such as cars, vans, trucks, trains. So it's going to be a higher demand of transport. Example, more cars. Now remember then, to explain it so we can pick up the second marks, we've got to say what's happened to cause this concentration of carbon dioxide to increase. So there's going to be more combustion. And we remember that combustion is burning of fossil fuels. .3. Explain why the increase in the world population may have caused the increase in the concentration of methane in the atmosphere. So we have to do the same thing, but this time we're changing the gas now. Methane. Why does methane increase in the atmosphere due to increase in world population? Well, where does methane come from? It comes from cattle and it comes from rice fields. Now, why would both of these need to increase if there are more people on Earth? Well, it's a higher demand for food. More people eating meat, more people eating rice. So higher demand for food. So more rice fields which produce methane. .4. Describe two potential effects of the increase in the mean temperature of the atmosphere at the Earth's surface. Well, this ultimately is discussing global warming. So, what are the effects, consequences of global warming we need to give to? Well, if the temperature of the Earth's surface is increasing, that can do many things. One of the main things it can do is it can lead to a loss of habitat. So, a place where animals may be living has been destroyed due to the temperature being too high for them to survive there. Another common thing that people think about when when we're talking about consequence of global warming is polar ice caps melting. Well, there are numerous. Drought is another example. 4.5. The mean temperature of the atmosphere at the Earth's surface has increased. Most scientists and our concentration of greenhouse gases on our x-axis, and our temperature is on our y-axis. It would essentially give us a graph like this, which is suggesting that as the concentration of these greenhouse gases increases, the temperature increases. But the problem is that this graph is just showing a correlation. But this correlation means that there's a link or a pattern between these two variables. What it's not telling us is that the concentration of greenhouse gases in the atmosphere is causing this temperature increase. And the reason why is because there are other factors which can cause an increase in the temperature. And that's the reason why some scientists are not going to accept this theory. So what this is showing one more time is that correlation is not showing a cause or causation. So that's the reason. There are other factors which can cause an increase. Question 5. Copper is extracted from metal ores. Chalcopyrite is a metal ore containing a compound with the formula CuFeS2. 5.1. CuFeS2 reacts with oxygen to produce copper 2 sulfate and iron 2 sulfate. Complete the equation for this reaction. You should balance the equation. So we need to figure out what is the missing reactant and then make sure that the equation is balanced. Well, let's try and do both of them at the same time. So for us to try and balance the equation, normally we should be writing the reactants out in terms of the atoms, and the same for the products. So in this reaction, we have copper, we have iron, we have sulfur. We should expect the same on the right hand side then. Copper, iron, sulfur. But we also have oxygen in our products. So we've already identified what the missing reactant is, because it needs to follow the conservation of mass. Now remember that oxygen has to exist as a diatomic molecule, so our formula is going to be O2. So we can add oxygen here. Now what we're going to try and do is balance the equation. So we're going to write the amount of atoms of each element underneath our equations. So for copper there is 1, for iron there is 1, for sulfur there's a 2, and for oxygen there is 2. For copper on our product side there's 1, for iron there's 1 atom, for sulfur there is 1 in copper sulfate and 1 in iron sulfate, so that's 2. And then for oxygen, there's 4 in copper sulfate and 4 in iron sulfate, so that's 8. So, looking at everything now, our copper and iron and sulfur are balanced. The only issue is that we have less oxygen atoms on the left than the right. So, we need to think now, what number can we put in front of our oxygen atom, which when multiplied by 2 will give us 8. Well, using our times tables, 4 times 2 is 8, So 4 needs to be in front of oxygen. (5.2) Calculate the percentage biomass of copper in CuFeS2. The relative atomic masses for our elements are shown. So, to find the percentage biomass, our formula for this is going to be RAM of element divided by RFM of compound, and then that needs to be multiplied by 100. So the element that we're interested in the question is copper. So our relative atomic mass of copper is 63.5. So what we need to do now then is find the total, which is RFM, of our compound CuFeS2. So that's going to be 63.5 plus 56 plus 32 times 2, because there are 2 atoms of sulfur. So 32 plus 32 is 64. So adding those up, we get our value of 183.5. So it's going to be 63.5 divided by 183.5 times by 100. So putting that in our calculator, we get a percentage of 34.6. (5.3) Describe a test to show the presence of copper-2 ions in a solution of copper-2 sulfate. Give the result of this test. So this is where we have to remind ourselves of our cation colors, which are part of our transition metals now. Well, if you go to our main channel and you find the community tab, you'll notice a picture of the different ions and the colors that you have to remember. So if you find copper-2, you've got a picture of the blue beast there. So copper-2 bright like the blue beast. So our result then is we're looking for a blue precipitate. Now what needs to be added to result in a blue precipitate? Well, to test for these transition metal ions, it's going to be sodium hydroxide solution. (5.4) Copper can be extracted from low-grade ores by bioleaching. Describe what is meant by bioleaching. Well, breaking down the word bio is using the environment. Leaching can be described as something that is going away or is getting removed from something. So when we're thinking about bioleaching and it's a low-grade ore, we're using a microorganism to do that, and that's bacteria. So whenever it's bioleaching, we're using bacteria. This is different from the other type of extraction method for low-grade ores, and that's phytomining. Whereas phyto is where you're using plants. But what is going to happen when we use this bacteria now? It's going to produce solutions that will contain our copper in this case. So using the bacteria will produce solutions which will contain the copper. Now, what are these solutions usually called when we're carrying out bioleaching? They're called leachate solutions.